In this video, we're continuing our work on Unit 3, Intermolecular Forces and Properties. Our objective is 3.3, Solids, Liquid, and Gases. The topic is to represent the differences between solid, liquid, and gas phases using a particulate level model, and our skill is representing data and phenomena. The first key point is that there are two types of solids, crystalline solids and amorphous solids. Crystalline solids have particles that are arranged in regular 3D structures. You can see here we have very ordered particles, and an example of this would be quartz, where it's silicon dioxide. So we have our silicon and two oxygens in this repeating pattern. We also have amorphous solids, which are particles that do not have regular orderly arrangements. You can see they're kind of messy. There's maybe different amounts of space in between different particles. And an example of this is glass, which is also silicon dioxide. And you can see that the spacing between the particles it's not like a neat crystalline structure like quartz. It's less regular. It's not regular at all. But both crystalline and amorphous solids have motion. Solids are constantly moving. They're vibrating. And so the individual particles, the motion of the individual particles is limited, and the structure of solid is influenced by interparticle interactions and the ability of the particles to pack together. Our second key point is that particles in liquids are in close contact with each other and continually moving and colliding. The arrangement and movement of particles are influenced by the nature and strength of the forces, polarity, hydrogen bonding, temperature between particles. So for example, this could be a liquid substance. And notice that every single molecule, there's always motion occurring, and they're in pretty close contacts with each other, constantly colliding. The arrangement of the liquid molecules depends on the polarity. So for instance, water, we know the oxygen is negatively charged, so it is going to be in close proximity to the hydrogens of an adjacent water molecule because there will be hydrogen bonding occurring. And then temperature also changes the structure. Where cold water, the particles are moving more slowly. So cold water is more dense than hot water. The particles will be closer together. Whereas hot water, the particles are moving more quickly. And so the volume increases slightly, the density decreases. Our third key point is that the solid and liquid phases for a particular substance typically have similar molar volumes because in both phases, the constituent particles are in close contact at all times. So here we have an ionic substance as a solid. It's in this strict crystalline structure, and when it's melted, when it's molten, you can see that these particles, there's a little bit more space in between them, but they're still very, very close. Here we have ice in the very strict crystalline structure, and when it melts and becomes water, it actually becomes more dense. You know, ice floats in water because the water particles are able to, some of those intermolecular rigid attractions break and the water particles are able to reform intermolecular forces. But steam, the particles are way more spread apart and even more so than image. And so I just want to show this. Here is a model of neon in the solid form. When I change it to a liquid form, the particles are still pretty close together, but now they're free to all sink to the bottom. But when I change it to a gas form, it really spreads out. The volume completely changes. And so neon is nonpolar. And the same happens with water. You know, solid water, it's in that crystalline, very strict structure. The particles are vibrating. And then when it's liquid, the molecules move a little faster, the temperature's increased, but they're still in very close proximity. But when it becomes a gas, they really spread out and the volume changes quite a lot. Our fourth key point is that in the gas phase, the particles are in constant motion. Their frequencies of collision and the average spacing between them are dependent on temperature, pressure, and volume. Because of this constant motion and minimal effects of forces between particles, a gas has neither a definite volume nor a definite shape. So here's our gas particles. They're really spread apart, and at high temperatures, they can move much more quickly, at low temperatures more slowly. So the volume can increase at high temperatures. It doesn't have a definite volume unless we would, if we cap this beaker here, then the gas would expand to take up that entire volume. And if we made it a larger beaker, the gas would expand further to take up that entire volume. So it never has a definite volume or a definite shape. And this kind of shows that at low pressure, it'll take up the entire space it's given. And when it's compressed at high pressure, those gas particles will move more closely to each other. So check for understanding 1. How would you draw a particle diagram for gaseous ammonia? So when liquid ammonia becomes a gas, what changes about it? So hopefully you recognize that really just what's happening is that these intermolecular attractions between these liquid ammonia particles, these liquid ammonia molecules, they'll break. And so now our liquid ammonia will still be NH3, but it will be more spaced out. So you would still have 6 particles in this box, but they would just be spaced out because those intermolecular forces have broken. What's one flaw in this model? So there are many, many flaws in this model, and I'm excited to read what you said. You could have said something like, there's no motion, motion's not shown. You could have said something along the lines of the sizes of the hydrogen versus nitrogen might not be correct. Ammonia is a polar molecule, so maybe they should be it should be more apparent which parts of the molecule are attracting to one another. Check for understanding 2. Of the following, the best explanation for the fact that most gases are easily compressed is that the molecules in a gas, so the molecules in a gas are in constant motion, so are the molecules in liquids and solids. And so that's not the best reason why they're easily compressed. The molecules in gas are relatively far apart, and so they can be easily compressed because there's a lot of empty space between adjacent particles. And so if pressure is applied, then those particles can move to fill that empty space and can be compressed. Have relatively small masses. Any molecule can be a gas, right? We can have water, H2O, as a gas, as a liquid, or as a solid. You can also have very large molecules as gases at very high temperatures, maybe. Have a real non-zero volume. They do not have a definite volume. Remember, gases can spread up and occupy whatever volume they're given. Move slower as temperature decreases. This is true, but this does not relate to whether or not it can be compressed. This is true of solid, liquid, and gases, and doesn't really relate to compression. So B is the right answer.